as to what actually is going on, and then there will be more efficient and sort of shortcut types of methods. So the least efficient way of graphing anything is a table of values. Okay? So that's the way we're going to start graphing this, and we're going to start by picking thetas to plug in and then coming up with the corresponding radius. So the thetas that we know the cosine values of are 0, pi over 6, pi over 4, pi over 3, and pi over 2. And that's just going to take us through the first quadrant. We'll get to quadrants 2, 3, and 4 afterwards. So when you plug in 0, what's the cosine of 0? 1 times 4 is 4. When you plug in pi over 6, what's the cosine of pi over 6? Radical 3 over 2. So that's going to be a 4 times radical 3 over 2, which will simplify to 2 root 3. When you plug in the pi over 4, cosine of pi over 4 is root 2 over 2. So that's 4 times root 2 over 2, which will be 2 root 2. What's the cosine of pi over 3? 1/2. 4 times a half is 2. And pi over 2, the cosine of pi over 2 is 0. 0 times 4 is 0. So these are the points with first quadrant thetas, and we will plot these. Now remember that your coordinate is technically r comma theta, okay? But I know in my own head, process theta first anyway. So there's a theta of 0, which is this terminal ray, and a radius of 4. So that'll put you 1, 2, 3, 4. That'll put you at a point right here. Theta of pi over 6 is this terminal ray. Now this radius is 2 root 3. So for the sake of knowing whereabouts that is, 2 times the square root of 3, we'll cheat and use the calculator here for a minute. Like I said, this is the least efficient method of graphing, so you won't actually ever probably graph this way on a test or a quiz because I will teach you more efficient methods. But that's 3.5-ish, just under 3.5. You're estimating anyway, so 1, 2, 3.5, it's right around there. And then pi over 4 pairs with a radius of 2 root 2. 2 root 2 as a decimal. I'm going to do this. Approximately 3.5 for that one, and this one's approximately 2.8. So pi over 4 with a radius of 2.8 puts us there. Pi over 3 with a radius of 2. And pi over 2 has a terminal ray right here, but the radius is 0, so that point is just at the origin. Now, when you connect points in polar graphs, they kind of get connected with curved, loopy type lines, and you'll see that more as we get a full graph done. But this, just connect the graph, those points, like that. Looking kind of like a semicircle. Yep. What do you mean by that? I don't know. Yeah, you're getting, if I even address that right now, you're getting like way ahead. So that's okay. That's okay. So we just went through our quadrant 1 angle. So now when we go into quadrant 2, we've got to keep going. Our next critical theta value is 2 pi over 3 that we'll plug in, followed by a 3 pi over 4, followed by a 5 pi over 6, and then pi. And these will be second quadrant ones. The nice part about where we are now is that we really don't have to fully reprocess plugging in like a 2 pi over 3, because 2 pi over 3 has a reference angle of what? Pi over 3. So the value is going to reflect the value that we already found the pi over 3 to be. The only difference is going to be whether or not this is positive or negative. So when we enter the second quadrant, all students, if we're taking the cosines of all of these, are they going to be positive or negative? Negative, because only sign should be positive. So the output for 2 pi over 3 is going to be the same as the output was for pi over 3, except for it's going to be negative. Do you follow? So that'll be 2 pi over 3 with negative 2. The output for 3 pi over 4 is going to be the same as the output was for pi over 4. It's just that it's going to be negative. So that'll be like negative 2.8 approximately. Ellie, what do you think is going to be the output for 5 pi over 6 based on the logic I've been... Good, negative 3.5. What is the reference angle of pi? What is the reference angle of this terminal, right? 0. The reference angle of pi is 0, so it's going to sort of reflect this one. It's just going to be negative. So negative 4 there. So when we plot these points, terminal ray of 2 pi over 3 is right here, but the radius is negative 2, so it's going to pop us backwards into the fourth quadrant. So 2 pi over 3 with a radius of negative 2, it's going to be right there. 3 pi over 4 has a terminal right here, but with a radius of negative 2.8, 1, 2.8-ish will be right about there. 5 pi over 6 with a negative 3.5, 1, 2, 3.5 will be here. And terminal ray of pi, but with a radius of negative 4, puts us back on a point that already had been plotted. Yes? So if I remember where I left off, this is where my table of values started, and I came this way. And if I keep going, we loop around here. And then we'll get into our third quadrant angles. Okay, so if I keep moving down into my third quadrant, the critical angles I need to look at there are 7 pi over 6, followed by 5 pi over 4, followed by 4 pi over 3, and 3 pi over 2. And again, I don't need to sit there and reprocess the value of cosine of all of these thetas and then multiply it by 4. 7 pi over 6 is going to have an output that reflects the output that pi over 6 was. Will it be positive, though, or will it be negative? Still negative. We're in the third quadrant where all our cosines will be negative. So 7 pi over 6 is going to be negative 3.5. 5 pi over 4 is going to reflect the pi over 4 value, but it will be negative, so negative 2.8. 4 pi over 3 will be negative 2. What's the reference angle of 3 pi over 2? Pi over 2, so it's going to reflect that, but it's going to be a negative. Negative 0, though, is still 0. So now we're in our third quadrant. Here's 7 pi over 6. But with a radius of negative 3.5, and what do you notice? We already have that point, right? 5 pi over 4 with a radius of negative 2.8. Already have that one also. It coincides with our first quadrant angles that had positive radii. Now we have third quadrant angles with negative radii, so they're all coinciding. 4 pi over 3 with a negative 2, already there. 3 pi over 2 with a 0, already there. So we started our table of values here. We went around, came back down, and now we're almost going around again and retracing all of our steps. Yes? When we move on to the fourth quadrant, cosines are going to be positive here. So we're going to have fourth quadrant angles of 5 pi over 3, 7 pi over 4, 11 pi over 6, and 2 pi slash 0. It's going to bring us back to the beginning. And what will our outputs be here? Positive or negative? Fourth quadrant cosines positive. Very good. So 5 pi over 3 is going to reflect pi over 3 exactly. That'll be 2. 7 pi over 4 will be 2.8. 11 pi over 6 will be 3.5. And 2 pi will be 4. So, fourth quadrant angle, 5 pi over 3 is here. Positive radius of 2. It's already plotted, right? All of these points in our fourth quadrant are going to coincide with our second quadrant thetas that were plotted with negative radii. So this is our graph. Okay, now that won't always happen. It just happens here because of the nature of cosine being positive in quadrants 1 and 4. Won't always happen, does here, so these are our points, and really to go around a full 2 pi, we kind of went around the circle twice, which you obviously can't see, but that's, given that we did this out the long way, that is what happened, okay? So now looking at that image, that's the graph of this polar equation. What would you say that's a picture of? A circle, right? And we just spent the last 2 days kind of translating polar equations into rectangular equations. If we were doing this in that fashion, what would we do to change this into a rectangular equation? Multiply by r on both sides. So we'd get r squared equals 4r cosine theta, which is x squared plus y squared equals 4x. And then this was like that supplementary video that I showed on Thursday, where we would complete the square to turn this into the circle format that it is. So I subtract my 4x over, and then what do I add to complete the square here? 4. So that'll be x minus 2 squared plus y squared equals 4. So now, because this is an equation we're more familiar with, this is the rectangular version, this is a circle centered at 2, 0, agreed, with a radius of 2. Does that make sense? Does everybody see that? Any questions? Again, like I said in the beginning, the longest, most inefficient way of graphing is to do a table of values, but it helps you kind of internalize what exactly is going on here, and then it can make you appreciate that shortcut a little bit more in turning something from polar to rectangular and then completing the square there. Okay? So down at the bottom, I also have a two-dimensional, kind of more traditional rectangular graph. And what I'm going to do here is plot the equation for cosine theta. So this is going to be like my r axis, and this is my theta axis still. So 4 cosine theta, as you all know, is just a cosine parent graph with an amplitude of 4. So I'm going to plot a cosine parent graph with an amplitude of 4, which means it's going to start at 4, end at 4, and then you're going to have a minimum at pi at negative 4 in your zeros. Okay, and then I want to look just at the first quadrant. So this right here is Q1. Because this graph is positive in quadrant 1, my quadrant 1 thetas have positive R values. Isn't that what we saw here? We're in quadrant 1, we have positive R values, which is why we have points in quadrant 1 here. Yes? Once our graph goes to quadrant 2, our quadrant 2 theta values yield negative R's. Yes? Hence the reason why we have nothing in quadrant 2. Because all of those quadrant 2 angles went and were paired with negative R values, which popped us visually over into quadrant 4. So far, so good? Okay. Quadrant 3, same thing happens. All of our quadrant 3 thetas yield negative R's. Hence the reason why on the polar graph our quadrant 3 has no points. They all yielded negative R's, which popped us back into quadrant 1 and really coincided with some of the points we already had. And then lastly, quadrant 4 theta values yield positive R's, which is why we actually have points in quadrant 4. Okay? I show you this because as we move forward and look at more polar graphs, not all polar graphs can be made into rectangular graphs that mean something to us. This one's nice because this rectangular graph means a circle, and we know that, but there's lots of polar graphs that don't look like something we're familiar with. If I show you just a random page, if you've looked ahead at all, we're going to be graphing stuff that looks like this. We don't have rectangular equivalents to a lot of this stuff. Circles are one of the few that we do. So not all graphs are going to be able to, have this shortcut. Yet we're not going to do this every time because that's way too long. And what you'll find is that we will use our knowledge of what the trig graphs look like to help guide us and take us on our shortcut to our polar graph. So I'm showing you that just not that we would ever need it in this particular problem because we do have the rectangular polar shortcut, but moving forward we will use the two-dimensional rectangular graph of the trig function to help lead us here. Liam.
So if we wanted to check our work, is there some way to graph polar equations on a polar plane on our calculators? Or no?
There is. There is. We'll get there. There's a mode that's a polar mode. Yeah. So we will look at that when the time comes. All right. So this particular graph, we could go through the entire table of values again. Maybe we will just for let's do it just for the first quadrant only. Just the first quadrant. Oh boy, you guys are really excited about this. 0, 5 or 6, 5. Who, Taylor? We'll do it just for the first quadrant, and then we'll see if we can play with the shortcut method. Because I don't think this one, think about that. Is there anything I can do if I multiplied by r on both sides? That would make this an r squared. which we could do x squared plus y squared, but it would create an r here that I don't think we want, and it would make 2r sine theta, which could be turned into 2y, but we would have an r on this 1 that we don't want. So this is going to be one where I don't believe there's going to be a way to go from polar to rectangular so that it's something we're familiar with. So when you plug in 0, what's the sine of 0? What? Sine of 0 is 0. 2 times 0 is 0. 1 minus 0 is 1. Pi over 6, sine of pi over 6 is a half. 2 times a half is 1. 1 minus 1 is, okay. Pi over 4, sine of pi over 4 is root 2 over 2. Root 2 over 2 times 2 is just root 2. So this is just 1 minus root 2, which I will give you a decimal equivalent for. 1 minus root 2. Negative 0.4. Sine of pi over 3 is radical 3 over 2. Times that by 2 is just radical 3. So this is just 1 minus radical 3, which has a decimal equivalent of negative 0.7. And then pi over 2. The sine of pi over 2 is 1. 2 times 1 is 2. 1 minus 2 is negative 1. Okay. So a theta of 0 and a radius of 1 is here. Liam?
Are we allowed to, like, change the amount that each thing goes by, like how we can in rectangular graphs? So instead of having each frame go by 1, we could have it go like 0.5. Is that, are we allowed to do that?
You can. So why don't we do that? So I just erased that point. So we'll spread it out to encompass these points and show it a little bit better. So he's saying, like, let's scale our radius. Rather than that being a radius of 1, we'll make this one be the radius of 1. And this one be the radius of 2. So that'll be like a half and 1 and a half. Are you with me? Are you with Liam? So a theta of 0 and a radius of 1 would be right there. A theta of pi over 6 paired with a radius of 0 is going to be a point that's where? At the origin. Pi over 6 with a radius of 0 is going to be right here. Now this is going to be the tricky part. How do I connect these points? It's not going to be with a straight line. Liam? Yes. That's one way of looking at it. So he's saying the next point is at pi over 4, which is here, negative 0.4, which is going to be, there's negative 0.5, so just prior to that first circle. So what is that? What do you think of that, Liam? Right, so that like up and around like here, to then come back down and catch that. Yes. Now the more of these you do, the more of a gut you'll have for that. Let's not connect them yet. If you have already, don't worry about it, but we'll come back to that, and I'm going to show you another logical reason why this is the way that we would go. Pi over 3 with a negative 0.7 is going, here's negative 0.5, so negative 0.7 would be there. And then pi over 2 with a negative 1 would be here. So we plot those points again and connect those points in the order that they occurred and kind of using a loopy effect. But let's jump down here, because this is the exact type of problem where we're going to have to use our two-dimensional graphing of trig as a shortcut. So this is a sine parent graph with an amplitude of 2, flipped upside down, and then shifted up 1, right? For all intents and purposes, this is the same thing as this. So where's our midline? 1. And it's a sine parent graph. So it starts at 0 and ends at 0, meaning starts on the end line, ends on the end line. Has a halfway point on the midline. But now with an amplitude of 2 and being negative, this is going to go and reach a minimum that's 2 units below my midline and reach a maximum that's 2 units above my midline. And there's a quick sketch for us. Okay? So if you look at this first sliver of the graph that's positive, okay, you started with this point. This was a theta of 0 and an output of 1. So this point, 0, 1, correlates with that point that we started with, a theta of 0 and a radius of 1. The first section of our graph, of course we're in the first quadrant, right? The first section of the first quadrant has positive R values. So when it comes time to connect these 2 points, we do know that there was a sliver of the first quadrant theta inputs that did have positive R values. Hence the reason that these looped through that quadrant just a little bit, right? Up until we get to pi over 6 and 0, which was that point, which on this graph must then be that point. That's the theta value of pi over 6 with a radius of 0. Once you get beyond pi over 6 to finish out that first quadrant, you have negative R values. See how we're below the x-axis and we are negative. So once we get beyond pi over 6, all of these theta values in here, they are all paired with negative R values, which is why this went back into the third quadrant. Do we see that? Now, when we enter the second quadrant, we are initially what? Negative. And so as we enter our second quadrant angles, we are initially going to be with negative R values. And if you kind of let this loop continue, it's going to go into the fourth quadrant, and that's backed up by this section here. We have second quadrant thetas initially with negative R's. So all of these second quadrant thetas that we initially get to have negative R's, which put us back in here. Okay? Rather than going through the table of values, let's look at our graph here. What other critical points do you see? Okay, so pi is our theta paired with a radius of 1. So pi is our theta paired with a radius of 1. Remember the scaling. So we have this critical point and this critical point that need to be connected. Yes? For the first portion of quadrant 2, we have negative R values, which is a section that's in going to be in the third quadrant. Isn't it true that at some point we reach a radius of 0? Right? So we have to loop this back around so that it catches the origin. this section on your polar graph correlates with this section on your two-dimensional rectangular graph. Second quadrant thetas with negative r values until you get back to 0. And then the very last sliver of your second quadrant thetas does have positive r values. So this very last sliver, as we get over to this point, is going to reflect second quadrant thetas paired with positive r values. Do we see that? Yes? Okay. Once we enter into our third quadrant, we have all positive r values in our third quadrant. So our third quadrant, Q3, if you want to label that, has all positive r values. We've just left off at this pi with a radius of 1, and we're headed in the direction of 3 pi over 2 with a radius of 3. So let's just plot that critical point. We won't worry about specifics of points in between, but 3 pi over 2 with a radius of 3, there's 1, there's 2, there's 3. Remembering the scale Liam came up with, which I think was a good one because of the 0.4, 0.7. But now a radius of 3 is going to be down here. So here's 3 pi over 2 with a radius of 3. See where our kind of loop effect ended off? Right there? We need to continue down to this point with a looping sort of pattern. So we don't need the specifics of those 0.4s and those 0.7s in between. We just kind of need to continue to our next critical point. And then as we move through our fourth quadrant, this whole section here is going to connect the point we just left off with the point 2 pi and 1, which we already have on the graph. Yes? So we're just going to continue through and end this there. And you can kind of round out your graph at the end. These graphs should never have sharp points. So if you feel like this came to too sharp of a point, you can always kind of round it out. And there's the graph of that. Keeping in mind that your fourth quadrant had all positive r values. That's the reason why in our fourth quadrant up here, we have all positive r values. Nothing negated and went back into the second quadrant at all. Does that make sense? Okay? So we could have gone through this one with a complete table of values. And on your homework, you can do it kind of in either way. You can do a table of values if you want, or you can use your two-dimensional sketch to guide you. Your critical points on two-dimensional sketches are going to be your same 5 critical points that you always have on one sine curve or one cosine curve, your midline intersections and your maxes and your mins. But also add in these critical points where you cross the barrier between positive r values and negative r values. So these true zeros, where anytime your radius is 0, your polar graph needs to make it back to the origin somehow. Okay? So briefly I will show you, you'll have the back of your book to check, but where is our mode? Under your function, you have a polar option, POL. Okay? So if you go to y equals, then it's going to say r equals. It's not going to say y equals anymore in the polar world. So 1 minus 2 sine theta. When you use that x, it's going to come up a theta. I think I might have been working with geometry kids, so I'm in degrees. I need to make sure I'm back in radians. Okay? Now, for our window, your theta min and max is going to be 0 to 2 pi by default. And your x min and max, this one goes from 0 to 20. We know that our radius really didn't go anywhere bigger than 3, was it? So I'll go 0 to 5. Let me rethink this. Window. Why did that just happen? Oh, maybe -5 to -5. Is that what you're saying?
Yeah, there's no. Well, there's a little bit.
Oh, -2 pi to 2 pi? Is that what you're thinking? I don't know what you're saying. You're saying, oh, no. Yeah, why am I not? Kyle, what are you saying? I did, didn't I? Oh. We have x's, y's, and thetas. Oh, 0 to 200. There we go. So I went -5 to 5, -5 to 5. Still set your x and y, so it's not really a one-to-one correspondence, but so I set that and then just went from -2 pi to 2 pi, although now I'm not sure that would matter, but yes. We won't be using this a lot because we don't have our calculators, but your calculator does do polars. You can use it as a checking mechanism, which is kind of cool. Questions on your homework? Anything from changing, I'm going to guess. How about the odd ones first? Were there any odd questions from Wednesday night's homework? Any odd questions? There are the answers to the evens. So take a look at those in the next couple minutes that we have to here, and let me know, are there any questions on any of the evens or any of the odds? Jalen. 66. Well, it's 66 is r equals 6 secant. So you put it over cosine. Cosine's an x. Anything else? Shoot, I thought you were going to have a question on which one? Yeah, Liam. Yes, the double angle ones, exactly. So our equations are r sine theta, not sine of 2 theta. So when you see a double angle, you need to get rid of it with your 2 sine theta cosine theta. Now, this whole number 2, you can divide that away on both sides. So if I divide by 2 and divide by 2, that's going to eliminate this and make this side a 2. And now this is just 4 things being multiplied. R times sine times cosine. You can rearrange this in any order Well, I'm going to put up a totally different one because I'm going to put the rectangular graph ones next to them. So you'll see them like side by side. Does that make sense? Like this. This is like our notes for Jalen. Our notes moving forward are going to have the polar next to the two-dimensional one.
See 'em, Jalen.
So I'll put one of those up next period.
Have a good day.
You too. Thank you. What's that? Yeah, no, sorry. Thanks, Nathan. You too. Hold on for 2. Yeah, quite the. Like, we didn't do this. Oh, no, maybe, you know what? Don't do it. Don't do it. Give those back. I changed my mind. I think I know what I was thinking. I think I know what I was thinking when I dumped this at the bottom of the pile. Girls, I just reneged.